Okay. Now, Sam Mugel will talk about quantum walks.
Hello. So thank you for having me here. My name is Samuel Mugel, and I'm a student from the University of Southampton and from ICFO here in Spain. With my collaborators, we've been working on an experimental suggestion for building a quantum walk with cold atoms. So to tell you a word about my field, I work with ultra-cold atoms myself. What we do, we build model quantum systems, and our tools for doing this are lasers and extremely cold particles. Now, the reason we use lasers is that they allow us to have extremely good control over very small particles. This, for instance, is an optical tweezer that allows you to actually grab hold of a single atom and carry it around. And the reason that we use very cold atoms is that when an atom's temperature is close to absolute zero, its quantum mechanical properties become important. So I will now introduce the normal random walk. If you imagine having a one-dimensional lattice and a particle starts out at a given position on this lattice, and what we'll do at every time step, we'll perform a coin toss, and the outcome of this will determine if the particle goes one step to the right or one step to the left. And mathematically, we can compute the probability of finding the particle at a given site after a given number of steps. This is what I've represented here. For a large number of steps, this probability is given by the binomial distribution. And what you can see is that it's what you can see is that it's strongly peaked around where the particle started, and it's very small around the edges of the distribution. I'll now introduce quantum walks. So on the left-hand side, we have the normal random walk that I've just introduced. On the right-hand side, I've replaced the walker by a quantum particle. Now, quantum particles have the peculiarity that they can be in several places at the same time. And so what's going to happen is that my particle, rather than choosing to go to the right or to the left, is actually simultaneously going to go to the right and the left at the same time. So you can see here that my particle starts out at a well-defined position, but at t equals 1, it's already on 2 sites. And at t equals 2, it has populated 3 sites. And repeating this kind of behavior, we obtain a quantum walk, which has extremely different properties from the normal walk that I spoke about earlier. Well, for instance, you can see that the probability of finding the particle at a given site looks very different from the one we had for the normal walk. In particular, it's almost 0 near to where the particle started, whereas it's maximal around the edges. And this is because back-traveling particles are going to interfere destructively. So we are interested in this type of system because despite them being very simple to understand intuitively, they actually hide some extremely complex physics. And in particular, we can generate what are known as topological bound states, which are these extremely interesting states of matter that are still very badly understood to this day. And there are also some experimental proposals for storing quantum data with this type of system. Thank you for listening. I hope you enjoyed this talk.